First, we have Cliff Kerr, and he's going to talk about Starism. So let's welcome our speaker.
All right, thank you, Alina. Thank you, everyone. So I'm going to talk about Starsim, which is a framework for modeling health and disease using agents. So we built it based on our previous experience doing disease-specific models. So a couple years ago at SciPy, I talked about the process of building CoViSim. So I'll briefly touch on that again, and then talk about what's been happening the last couple of years. We've designed it to be easy to use. We've already conducted a few training sessions for it, and we have about 200 people who are trained, not all active users, but that's where we're starting to build the community. And I will also just want to preface this by saying that this is still very much an in-process project. We very much appreciate that the SciPy organizers believed in us and gave us this talk, even though version 1.0 was released technically very early this morning. So what you're seeing is very fresh, a little bit raw around the edges, and we would love to collaborate or have input. I just wanted to ask a couple questions. Who here has done anything with agent-based modeling before? Okay. Couple people, literally a couple people. Who here has done anything with disease modeling before? Okay. All right. Who here has used Python before? Okay, cool. That was a unit test. It's unit test passed. So I'll keep it a little bit general, but I'll also try to show what makes Starsim a bit special. So first, I'll talk about the motivation, the genesis, like where we got to where we are now. A little bit about the design and implementation of Starsim in terms of the code. I'll talk about the first application we've used it for, which is modeling syphilis and HIV co-infection, and then wrap up. So I'm at the Institute for Disease Modeling, which is part of the Bill and Melinda Gates Foundation, or now known as the Gates Foundation. And our role is kind of to coordinate the development of the software. We've been building open source software for almost 20 years now. And so this is our latest effort to sort of continue that process going, and if not move into the future, at least stay in the present. Up until March 2020, most of the IDM's work was based on this model called EMOD, which stands for Epidemiology Modeling Software, which is this huge, enormously powerful thing written in C++, can only be run on an HPC. Wonderful if you want to know about eradicating malaria in Mozambique or something like that, down at the local government level. But not really very suitable for something like COVID, where we were all encountering it the same as all of you. Like, we'd wait for the evening news report to see how many new cases there were, like what the latest about transmission was. Don't wear masks because it's fomite transmitted. We all remember those days. So we needed something that we could adapt really quickly, and so obviously this giant C++ model wasn't suitable for that. So we decided to basically start from scratch and write something in Python instead. So that model is called CoViSim. We intentionally tried to make it as simple as possible, as flexible and easy to use as possible, because we had no idea what the next question was going to be. When a vaccine was going to be ready, when the diagnostic was going to be ready. So we had to have it very flexible in order to answer questions as they came. And of course, the timelines were just insane, as you probably either remember or can imagine. Something new would come out, in the morning, and then the government would want an answer by that evening of what they should do about it. But as fast as we were, it was also really important to be rigorous, because literally thousands of millions of lives were at stake, and so if you had a sign error in your code, that was not great. So we really tried to balance both the speed of development and the rigor, and thankfully we had a big team who came together for the purpose of doing that, and we did all right. So the questions changed over the course of the pandemic. So early on, there were questions about testing and tracing, how many infections would happen if we opened up more. Then there were lots of questions about schools. Should they be closed? Should they be open? And then about borders. So some countries like Vietnam and Australia, where I'm from, basically stopped COVID by closing the borders, but that became less and less sustainable over time. And then the questions got more complicated, more subtle about what's the impact of different variants. If you got a wild-type infection and got one vaccine, but then missed the second dose, and then what's your immunity? So the questions started getting quite complicated. But COVASIM did end up getting used pretty widely globally. So this is a pretty good map for disease modeling software. Obviously, if you made a map like this of like pandas or something, the entire world would be green. But for this niche, pretty niche software, we were pretty happy with how quickly it became widespread. Less happy that everyone suddenly needed to model this like terrible pandemic sweeping the globe, but it was good for our download stats. So the structure is that, so it's an agent-based model, and so what that means is that it simulates the states of individual people over time. This is in contrast to what are called compartmental or rate-based models, which are instead based on differential equations. So most epidemiological models are compartmental models. They just say, they have a list of equations. It's like, your probability of getting infected is this, and you integrate the equations over time, and then you get your answers. COVASIM and Starsim are agent-based models, which mean that we track individual people. So we can say, this 46-year-old woman is living in a household with 3 other people. She goes to work. And then she has these other connections, and then what's her probability of infection? You no longer need to just use these kind of like abstract rates. You can say, for this individual, with all of the different heterogeneities that individual has, what is their exact probability of infection? So in an agent-based model, the fundamental calculation that gets done is a probability that a given agent on a given time step will change from one state to another. So in disease modeling, this could mean the probability that they go from susceptible or uninfected to infected, the probability that they get tested and so go from undiagnosed to diagnosed, or that they go from being ill with a disease to being dead. And the other really critical thing about agent-based models is that they happen on networks. So agents just sitting around by themselves don't really do much of anything. It only becomes really interesting when they interact with each other in networks. And I'll talk a little bit more about that later. But for COVID, we were thinking about these contact networks in terms of household, school, workplace, and community. But in Starsim, because it's more general, we look at other types of networks as well. So for example, I'll show an example of sexually transmitted infections. So there, of course, sexual networks are the most important. So this shows how things have kind of evolved from our initial work on COVASIM towards this generic Starsim package. And yes, Starsim is just an in-joke, meaning like the star is an asterisk for all different kinds of diseases. So we started off implementing these disease by disease. We started with COVID, family planning, HPV, and then at this point we started thinking, okay, it would be really nice to have a framework. So our more recent models we have been implementing using the Starsim framework. And so the terminology is a little confusing. The Starsim framework refers to the code base, like what you get when you type pip install Starsim. The Starsim suite refers to all of these models. So I'll just say a little bit more about that. So initially we started off with this minimalist idea that we could just have like separate code bases for every disease with a kind of common set of design principles that underlie them. And then there are other people in the team who are arguing that we should have one code base that did every disease. So this is how our previous software, eMod, had been written. And then, of course, you can have something in the middle. You can have an interlocking set of modules that provide different things. And these are not discrete choices. It's kind of a continuum from one end to the other. So initially, we thought that we were going to head towards that. And we started from there. But now we're kind of in the middle, and we think that's the right place to be. So this shows the overall architecture of Starsim. So the sort of key chunks of it are, firstly, there is a people object. So this stores all of the different agents and their states. It also stores the network, so how the different agents interact, and the demographics, so how the agents update. So agents can become pregnant, give birth, die, and things like that. And so all of that is customizable. And of course, this is intended primarily as a disease model, although I'll come back to that later. And so each disease has a separate module that can be implemented. So these are just some of the ones that we've implemented already, but we've tried to make it flexible so you can implement more or less anything. And then one of the really key differences between Starsim and other models is that most other disease models only do one disease at a time. So they might do HIV, or they might do syphilis, and they might even do HIV in the context of a syphilis prevalence, because having syphilis changes your probability of getting HIV. But what almost no models do is allow both of these diseases to be modeled simultaneously. And because Starsim does allow that, what that means is that if, for example, you treat syphilis, then that will also change what happens with HIV. And this is something that most models can't capture. So we have these things called connectors, which let the different disease modules talk to each other. So you could just run an HIV simulation, or you could just run a syphilis simulation, or you could have both of them in your model and then connect them together. Now, practically, usually when people do disease modeling, it's to look at different scenarios. And the most important thing with different scenarios is interventions. Policymakers want to know things like, what if we increase the coverage of this vaccine? What if we develop a new, more accurate diagnostic or something like that? Starsim has a fairly built-out library of different interventions, and again they're very customizable. There are also what we call analyzers, which are also sometimes called reporters, which is that there's a lot happening in the simulation at every time step. There might be tens of thousands or hundreds of thousands of agents, and they're all interacting in different ways. And it's far more data than you could or would want to export. And so what analyzers tend to do is they pull out the things that you actually want to know about the population at each time step. So maybe you want to know, the age distribution at which people tend to get infected and things like that. And finally, for the default results, there you can plot, export, do all the sorts of things you would want to with that. And just one other point I wanted to make here is that sort of the key power of the Starsim architecture is that the people object is shared across all of the diseases. So each disease has its own states, but then these are accessible to all of the other diseases. So even though HIV and syphilis, for example, are implemented in two separate modules, the HIV module can see into the syphilis module and see if a given agent has syphilis and update the calculations accordingly. So I wanted to emphasize that we've really tried to take a user-centric approach to designing Starsim. And so the reason is twofold. Firstly, even though the Institute for Disease Modeling is based here in Seattle, we don't, that's not where the burden of disease is. So we very much want to sort of shift the focus of the modeling from Seattle, from the global north, to places where they actually need more of this modeling work. So you saw on the first slide, we just did a workshop in Nairobi, but that's kind of our target audience. Not you, I'm sorry, but people who really don't have a lot of these tools already and could use something like this. We also, as much as possible, want the software to kind of get out of the way. All of the science here is so complicated anyway that even if the software completely gets out of the way, it's still going to be really complicated to model it. But as much as possible, we want people to have a scientific idea. It's like, hey, I wonder what would happen if my vaccine was had a property like this, and as simply as they can conceive it, implement it into the model without worrying about writing too many methods or lambda functions or anything else that a kind of bread and butter epidemiologist is probably not going to be familiar with. Another thing that we found has been really important in this situation is about trust. So we want users to trust us, that all of the science that is in the models is based on the latest literature and has been double-checked and validated, but also that we trust them. We make all of the models open source. We say, go ahead and use it. We trust you to build what you need from this framework. So the basic philosophy behind the Starsim suite is that common tasks should be simple. So there's certain things that you always need to do when you're defining a simulation. You always need to define parameters, run the simulation, and plot the results. And that will get you pretty far. So on the right here is an example of CoViSim, which shows these three things. You can create the simulation, run it, and plot the results, and you just get default results. Of course, this isn't useful for policy, but it provides a starting point that you can say, oh, well, actually, in my case, my prevalence is a little bit higher, my transmission is a bit lower, and then it gives a starting point that people can modify it to what they want. But the flip side of this is that while uncommon tasks can't always be simple, they should still be possible. So again, modeling diseases is incredibly complex. Every single person wants to do something at least slightly different, whether it's a different demographic input or a slightly different disease model. And so we wanted to make it as flexible as possible so that everything is still possible. In terms of implementation, another thing that has been a limitation of a lot of agent-based models is they tend to be incredibly slow, especially in Python. And the reason for this is that they tend to be implemented in this loop-the-loop method. And so you loop over every time step, and then you loop over every agent, and then you loop over every state, and then you update it. So for a kind of typical numbers where you have 700 time steps, like 2 years with a daily time step, 30,000 agents, and maybe 30 different states, you have to do that update step a billion times. And so this is very simple conceptually. It's all just if statements and for loops and so forth. This is an example from our family planning simulator before we updated it, but is incredibly slow. So the alternative is something that we came up with that we call arrayification. Where basically instead of storing each agent separately, instead you simply use NumPy arrays for each state, and then instead of each agent being an object, they're just an entry in a NumPy array. You can think of it like a data frame as well. So the columns of the data frame are the states, and then the rows are the different agents. We don't actually implement it as a data frame for performance reasons, but it's equivalent to that. And so there are two advantages of this. Firstly, it's up to 100 times faster, which is pretty nice, but it's also even shorter code. Sometimes the individual operations can be a little bit more complicated because you might be doing a set operation instead of an if statement to pull out the indices that match something. But when you get used to it, it's pretty efficient. And so this is what it looks like from benchmarking, and in this particular example, when we implemented it, it was 70 times faster. So that's pretty nice. So what does that look like? The left is the original, and the right is the new one. So it's pretty nice, to have the one on the right instead of the one on the left. So this just shows kind of schematically what these two different things are. So most agent-based models are implemented in this kind of object-based framework where each agent is an object that has all of their different states. And what we've done instead is we have done this array-based thing where each state is a NumPy array, and then each agent is an entry within the NumPy array. And this gets very complicated when people die and people are born and things like that. So I won't go into the details of that, but we figured it out, we think. And so practically what this means is that you can, on a typical laptop CPU, you can run about 7 million person days per second, and each person takes about 10 kilobytes. And the last thing I want to say about the performance is that under the hood, we use a library called Cyrus to simplify a lot of the common tasks of scientific computation. So I know that font is very small. I'm sure you can't read anything, but basically what this is doing is it's just creating this kind of like random wave function where the amplitude of the noise increases over time. So without Cyrus, you have about 7 lines of imports. With Cyrus, you can do it all with 1. To run in parallel, there's a cyrus.parallelize function, which does it in 1 line. Otherwise, you'd have to import multi-pool and create a pool and run it and close it and join it. To save, again, you can do that in 1 line with Cyrus, whereas if you want to use gzip, then that's going to be about 5 lines. Same with loading. And then to plot a surface, Cyrus uses defaults wherever possible. And so, again, if you just have a 2D array of data and you want to make a 3D plot out of it, you can just say surf 3D, and it will assume you want a x-axis and y-axis to be integers and things like that. All right, so I'll skip over the example pretty quickly because there are only a few minutes left. But there's a very large burden of STIs. So there are about a million pregnant women with syphilis in 2016, and a huge proportion of these women end up with adverse birth outcomes, so about 1 in 3. So there's a huge burden of disease for syphilis. There are lots of policy questions about how we could control syphilis better. So what if we had better diagnostics? What if women who go to antenatal clinics for pregnancy checkups could get better access to testing and treatment? And then which populations are most important to target? So all of these rely on some data, but they're also partly modeling questions. So this shows an example of the connector between HIV and syphilis, and showing that you get very different results depending on whether you include the bidirectional increase in risk between HIV and syphilis or whether you don't. And then this is kind of the key result, which is that showing that if you treat syphilis, then obviously you get a very big reduction in the number of syphilis infections, but you also get a significant decrease in the number of HIV infections. And so this is basically why we wrote Starsim, because no other model of HIV or syphilis that we know of is able to capture these kinds of effects. So just to summarize, we haven't talked about calibration or validation. These are very important components of actually using one of these models in practice. There is built-in calibration based on the Optuno library, but in practice it can require a lot of work to get it to work. As I mentioned, this is very new, very fresh. So if you are interested in this, we'd love to work with you. And one open question that we're still struggling with at the moment is that we're disease modelers. We developed this very much based on the idea of modeling diseases. But then after we wrote it, we were like, actually, this is kind of just can be used for any agent-based modeling question. So we're still debating whether to pivot and whether to lean into that more, whether to keep it more disease-focused. But if you're interested in agent-based modeling in general, I'd be curious to chat with you. Okay, thank you very much for your time. Yeah.
So you talked about the connection with syphilis and HIV. Have you found any unexpected connections? And also, how do you like verify where a connection is from, just like quantities of data?
So the question is if we found any unexpected connections between diseases and how to verify or validate those connections. So we haven't found anything too surprising because the logic of the connections are things that we program in ourselves. We have found no like sort of, oh my God, this is incredible kind of surprises, but we have been surprised in both directions. We have been surprised that in some cases it makes less impact than we would think, just from the kind of linear operation. In other cases, it's had more impact than we would expect. In terms of validation, one of the nice things about this is that when you calibrate the model to the data, of course, in the real world, you do have co-transmission. You do have diseases that are co-transmitting together and affecting each other and so forth. And so a lot of other models have struggled to calibrate to these data because it's difficult to calibrate to HIV data if you're not also calibrating to syphilis data. And with Starsim, we can calibrate to both simultaneously. And so through that calibration, we can sort of if we get both right, then it validates both aspects of the model. Whereas if you were to calibrate a model just to the HIV data, for example, then you basically have to insert a syphilis fudge factor because you're not calibrating to it directly.
Read a quick question from online. So we have Kerr who asks, how large of a model can you run with Starsim? If you're using the Pi under the hood, at what point does that alone stop being feasible? Is there support for hardware acceleration for larger simulations?
So the question is, how large of a simulation can you run? When does it stop being feasible? And is there support for hardware acceleration? So we have run simulations, kind of test simulations of up to about 1 billion agents. So that's all fine. We have investigated doing some of this work on GPUs instead of CPUs. So we've left it at CPUs for two reasons. First, it's kind of fast enough, and second, we want to make it as, again, flexible and accessible as possible. But especially for some of the network stuff, which that's a very GPU friendly kind of operation. We do use NetworkX under the hood, so we're continuing to explore that. The other answer I would give to that is that when you have very, very large numbers of agents, unless you also have very, very large amounts of data, you don't really have much additional benefit. The agents, you're kind of getting closer and closer to a compartmental model, and as long as you have kind of 10 agents in any one category, you don't really need that much more than that. You certainly don't get any benefit from having 10,000 agents in each category instead of 100 or something like that.
So based on the description of your array implementation, I'm assuming that every time step, essentially you update everything at the same time based on kind of previous time step state, right? Is there any situation where you have dynamics that are fast enough where like the order in which you update agents matters? And if so, is that covered under the stuff you protocol?
So the question is how whether all agent states are updated on each time step, and whether there are dynamics that happen fast enough that require different or faster time step. That's a fantastic question. It didn't make it into the 1.0 release, but the next release we're planning on addressing exactly that, because sometimes we want to model different diseases that have incredibly different timescales. So for example, we want to model respiratory syncytial virus, which is an important disease of childhood, which it's like a common cold. It has a time frame of like a few days to a week or something. But because it affects young children, we also need to model births, which do not happen on a time scale of days. And so we have this kind of like multi-year time scale of population growth coupled with this really fast, like, several day transmission cycle. So at the moment, there's just a single integration time step, but we're working on doing exactly that. So each disease can have its own little internal clock.
I think we have time for one last question if there is one.
Anybody else raise their hand? Okay, cool. Can you talk a little bit more? You say that it's very important to get involved kind of at the ground level. Could you talk a little bit more about, you said you visited, the team visited Nairobi. Could you talk about what that kind of looks like when you go there and what happens?
Yeah, so we've been working on epidemiology software and doing trainings for about 15 years now. And the reason why it's so important is that decisions don't get made in Seattle. They get made in Nairobi or Bangkok or something like that. And so what we want to happen is we want there to be people in Nairobi or Bangkok or Dhaka who understand the modeling, are able to do the modeling, understand the data. They can say, no, I don't trust that data source, but this one is really good. And then that is much more likely that policy decisions actually get made. Because if we just sit here, we have no idea what's happening on the ground there, and we can write our fancy models, but it's not going to have much impact in the real world.